In this video, we will be talking about related rates, how to find them, what they are, and in general, just the strategy of finding them. This is 2.7 in your books. If you want to follow along, this is pretty close to it. These notes will also be in OneNote if you are my student. They'll be in the content library. Okay, so two objectives for this lesson, and that is finding a related rate and using related rates to solve real life problems. And that sounds really, really simple, but this can often get a little bit overwhelming and a little bit more challenging than it often seems like it is. So, in order to do that, there's a couple of things I need us to remember. So, we need to be able to take pretty much any derivative I throw in front of you. So everything from the derivative of a constant all the way to the derivatives of arcsine, arccosine, and arctangent. Some of those will be used quite a bit. Some of them won't be used at all. You will never see them in reference to a related rates problem, or at least they're very rare. Okay, but you'll kind of see as we go along what's going to be used most. And we also need to know basically what a derivative is. Okay, so a derivative is just going to be some rate of change. That's it. So if something is changing, there is some derivative that exists, okay? And that might come in the form of just a number, it might come in the form of an equation, it might be some dr dt or df dt or whatever, but it is a rate of change. It is a derivative, okay? The next important thing that we really need to understand how to do is use implicit differentiation. So in yellow, basically in general, if we are taking a derivative with respect to, in this case, t, of some other variable, in this case x squared, if those two don't match up, so if this t doesn't match this x, we need to use the chain rule. Okay, so what I mean by that is we're going to implicitly derive this. So the derivative of x squared, that outer function, that's 2x, times the derivative of the inner function, because x is some function of t. So we have to put the dx dt in there. Okay, this is different than the derivative of x squared with respect to x. That would just be 2x. Okay, so if that denominator of the derivative, if you want to call it that, doesn't match what's inside, then we have to use this implicit differentiation. Okay, so just some examples so we get warmed up. The derivative of tangent of y, well, that's going to be secant squared of y, because that's the outer function, times the derivative of y with respect to x. Okay, something we're going to see quite a bit is finding dv dt for v is equal to s cubed. All right, and if you're reading below, you can already tell this is a volume of a cube. But if we want to find dv dt, we have to take d dt of both sides. And it's going to look really similar to what we just did. So dv dt, that's just dv dt. That's the change in volume over time. The derivative of s cubed, that outer function, is 3s squared, times the inner function, that derivative of s, so ds dt. And honestly, that in a nutshell is a related rate. You don't know what that is yet because you don't know what it looks like. But if you're able to do that, you're able to find related rates. It gets more complicated than that, but that's basically it. Okay. Besides that, there's some formula, volumes, whatever, that you just need to know. And there's a list of them, and you can read through it. Things I want to kind of draw your attention to. We're going to use volumes quite a bit, and there's some volumes that you probably haven't seen in a while or ever. So volume of a sphere, you might have seen at some point, that's 4/3 pi r cubed, where r is the radius. There's a volume of a cylinder, which shows up quite a bit. That's pi r squared times h. R is the radius again, h is the height. Okay. Volume of a cone, that's going to be one of the first examples we see. Pi thirds times r squared times h, where r is the radius and h is the height. We also have to be aware of these things about right triangles. Okay, so Pythagorean theorem, that shows up. All of the sine, cosine, and tangent functions show up, and we just need to know what those are and what they reference. One question that shows up in the homework has to do with similar triangles. So you need to know that the ratios between similar triangles and those sides is going to be constant. Okay, so in this case, big A over small a is going to be equal to big B over small b and big C over small c. Okay, and that's going to remain constant. There is going to be one homework question that refers to that. So what is a related rate? Well, a related rate is really just something, it's a rate that relates to another rate. That's basically it. Okay. So what we're going to get are equations where one rate is related to another rate. Okay, so we're going to get different rates, and we're going to have to solve for one of them. So kind of a classic example of this is this conical tank. And this tank, and this is a kind of a simple version of something that happens in real life. This conical tank is filled with water. Okay, and as water drains, things are changing about the shape of this cone, or at least the water inside the cone. Okay, so things that are changing as water drips out. All right, we have to think about this. So when water drips out, this level, this height, is going to go down. So there's going to be some rate of change of height. Other things that change are the radius of this water, right? So as water drips out, the radius is going to get smaller and the height's going to get smaller. And both of those things are going to be related to the change in the volume of the water. Okay, so how do we kind of put that all together? Well, we have a volume of a cone that is V is equal to pi thirds r squared times height. Okay. And to get all of these rates of change, we would take the derivative of both sides with respect to t. Okay, if we do that, we get dv dt, that's like the easiest bit, time, or is equal to, and then pi thirds is a constant, so I'm going to leave that out. The derivative of r squared times h, and that's a product, so we have to use the product rule. So 2r dr dt times h plus r squared times the derivative with respect to t of h, which is just dh dt. Okay. All of these rates are related, hence related rates. And for questions regarding this, you will be given enough information to solve for one of them. And that's the whole idea. That's what all of these questions are going to look like. Some are very, very simple. Some require a formula which you may not have seen ever or in a while, that might need to be looked up. But most of them are up above if you look back at those notes. Okay, so that's a kind of a classic example. Let's do a really, really simple example. Okay, so the variables x and y that are both differentiable functions of t, right? So x equals some function of t and y equals some function of t, but we don't know those functions. These are related by this equation, y equals x squared plus 3. Okay, and we want to find dy dt, and we are given that x equals 1, and that when x is 1, dx dt is equal to 2. Okay, and that sounds like a lot, but in general, it just means take the derivative of both sides and then plug those things in. Okay, so if we take the derivative with respect to t of both sides, we're going to get dy dt is equal to 2x dx dt. Okay, and now we have enough information to solve for dy dt. We have x equals 1. And when x is 1, dx dt is 2. So this dy dt is just equal to 4. Okay, really simple related rate, but hopefully it gets the point across. You're taking the derivative with respect to time or something else on both sides. You're going to derive those things implicitly and then plug a bunch of things in and solve for the unknown that we're looking for. A little bit harder of an example is this pebble being dropped into a still pond. Okay, so in this example, a pebble is dropped into a pond or a pool of water causing these ripples in the form of concentric circles. And the radius r of the outermost ripple is increasing at a constant rate of 1 foot per second. Okay, so we have that this distance, this r, is increasing at a rate of 1 foot per second. So that's that derivative dr dt is equal to 1 foot per second. We are also given the radius is 4. So when the radius is 4 feet, at what rate is the total area of the disturbed water changing? Okay, so we want to find the rate of change of area. Okay, and we want a formula that has dA dt, dr dt, and r in it. Okay, so we have to start from the area of a circle. Now the area of a circle, if you rewind a little bit or just remember, is pi r squared. Okay, and we need to take the derivative with respect to t of both sides. So dA dt is going to be equal to 2 pi r dr dt. Okay, pi is a constant, so you can ignore it and just multiply it out front. Okay, so we have stuff that we need. We have r and we have dr dt. So if we plug those in, we get 2 pi times r, in this case, what did I say? 4 foot. Times dr dt, which we said is 1. So then dA dt, if we multiply those things together, is just going to be 8 pi feet squared per second. Okay, I'm not as worried about the units again, but they're always helpful to have. Okay, so just reiterating what we're doing, we are labeling what we have, labeling what we need, making or finding an equation that has those things, implicitly deriving, and then plugging in and solving. Okay. So another kind of classic example is air being pumped into a balloon. So in this example, air is being pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. Okay, so find the rate of change of the radius when the radius is 1 foot. Okay, so we have air in this balloon, which is just a volume. Okay, so we are given the rate of change of that volume. So we are given dV dt, which in this case is 4.5 feet cubed per minute. And we want to find the rate of change of radius, so we want to find dr dt, that's our unknown, when r is 1. Okay. So we need an equation with dV dt in it, dr dt, and r. Okay, so we need to start from some equation that when we take the derivative of that, we get those things. Okay, the only equation I know with r in it and v is going to be volume is 4/3 pi r cubed. I want to double check that. Yeah, 4/3 pi r cubed. Okay, and when we derive with respect to t on both sides, we get dV dt is going to be equal to 3 times 4/3 pi times r squared times dr dt. Okay, that 4/3 pi is a constant, so we can just leave it. Things are going to cancel. So we get dV dt is equal to 4 pi r squared times the rate of change of radius. Okay, so now we had the equation. We implicitly derived that equation. And now we have stuff to plug in. Okay, so we have dv dt, that's 4.5. That's going to be equal to 4 pi times radius, when in this case is 1, times dr dt, and that's our unknown. So all we have to do is to take 4.5, divide it by 4 pi, and that's going to give us dr dt. And that will be in feet per minute. Okay, again, I'm not as worried about units right now. I just want you to understand kind of the concept and how to do it. Where this gets a little bit harder is when we're not explicitly given or have an equation that gives us everything. Okay, so in this case, an airplane is flying on a flight path that will take it directly over a radar tracking station. So it is going this way. The distance s, this distance, is decreasing as that happens. And it's decreasing at a rate of 400 miles per hour when s is 10. So when that distance is 10. So what are we given? Well, we're given ds dt. That's negative 400 miles per hour. And we're given s is 10. But we don't know much else. Okay? What we can assume from this, though, is that because this plane is flying directly over, this rate is not changing at all. So that vertical height, that's going to remain constant at 6 miles per hour. So we can call this like b or something. dB dt is nothing. And that's not even going to show up, and I'll show you why here in a second. Okay, so we need an equation where we can get sx and dx dt and ds dt involved. All right, so we have this equation. We have 6 squared plus x squared is going to give us s squared. That's Pythag, okay? And this is going to show up quite a bit. So first thing we need to do is we actually need this distance right here, because that's going to help us out later. All right, so we just need to solve for x in this equation by plugging in stuff. All right, so 36 plus x squared is going to be equal to 10 squared. If we solve this, we get x is equal to 8. Okay, now we have ds dt, we have s. This thing isn't changing, but we also have a b, I guess, if we want to call it that. And we have an equation. All right, so we're going to take this equation, we're going to implicitly derive it, and then we're going to plug stuff in. Okay, so if we take the derivative of this thing on both sides, we get 0 plus 2x dx dt is equal to 2s ds dt. And now we have an equation where we can plug in all the knowns and get the unknown. Okay, so 2x, that's going to be 16 dx dt equals 2 times 10 times negative 400. So dx dt is equal to 2 times 10 times negative 400, all divided by 16. And if we simplify this, we should get negative 500. Yep. And this would be negative 500 miles per hour. All right, which means this plane is going in this direction at negative 500 miles per hour. Okay, so again, it's the same process, but we have to be a little bit clever sometimes with how we get all of the knowns. So we had to do a little bit of work to get this known. Actually, that's given to us. We had to do a little bit of work to give us this known. and then plugins, and then implicitly derive and plug in stuff. Okay. Where this gets a little bit harder is when we have to start to introduce trig. Okay, so in this example, a television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position equation. S is equal to 50t squared, where S is measured in feet and t is measured in seconds. The camera is 2,000 feet from the launch pad, which is constant. We want to find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. So we are trying to find the rate of change of theta, which is d theta dt. So let's just mark that as the thing we're trying to find. So d theta dt is what we are trying to find. Now, because it's an angle, we're going to have to do some type of trig to get there, because we are only given components of a right triangle. Okay, we have that t is 10. And from that, we're going to find a couple of things. So if t is 10, this s is 50 times 10 squared, which is going to give us 5,000. And we also need an equation for theta with s and the adjacent side, because that's all of the stuff that we're given besides the time, which we just used. Okay, so the only equation with an opposite side and an adjacent side with an angle theta is tangent. And that's going to be s over 2,000. Okay, so if we start here, we should implicitly derive this stuff. Okay, so if we take the derivative with respect to t on both sides, we get secant squared of theta, d theta dt is going to be equal to 1 over 2,000 times ds dt. And now we run into something that, again, we don't have immediately, but we can find it. Okay, we are given that s is equal to 50t squared. So if we take the derivative with respect to t on both sides, we get ds dt is equal to 100t. And we can just substitute that in up here. Okay. In order to start to make things simpler, I'm going to change secant into 1 over cosine. So this is 1 over cosine squared of theta times d theta dt is going to be equal to 100t. I'm sorry. 100t over 2,000. Okay, so that's just substituting in what we just found here into ds dt, and then over 2,000, that was right here. Okay, then d theta dt is going to be equal to 100t times cosine squared of theta all over 2,000. Now, we are not explicitly given what cosine of theta is, but we can find it pretty simply. All right, cosine of theta, and I'll do that over here, is going to be this adjacent side, so 2,000, over the hypotenuse. Okay, and the hypotenuse, that's just going to be the square root of that s side squared plus 2,000 squared. Okay, so if we start to substitute that in again, d theta dt is equal to 100t. I'll write this as a separate fraction. And then that cosine squared of theta is going to be this cosine of theta all squared. When we substitute things that we know in, right? So we know t is 10 and we know s is 5,000. We get d theta dt is equal to 100 times 10 times one of these will cancel one of those. So 2,000 over s squared. So yeah, 5,000 squared plus 2,000. That should also be squared. Okay, that square is going to cancel out the square root. And then one of these 2,000s is going to cancel one of the 2,000s on top. Okay, and when we simplify that, we should get 2 over 29. And this will be in radians per minute. Okay, so again, a little bit harder because there's more things we have to find on the way that were not immediately given in the directions. Okay, this is a harder problem. I understand that there's trig involved. I get that that makes it even harder. But this is like the kind of logic that I would expect a little bit later on. Okay, what we're doing is we are labeling what we know or what we need to know. And from that, we're just coming up with a way to get d theta dt and then filling in everything else. Okay, that's kind of the name of the game. All right. So in general, and we're gonna do some examples in class, and there's some examples on the homework. But in general, we're gonna follow these guidelines in order to answer related rates problems. We identify all the given quantities, and we're going to identify the thing that we need. Usually it's really, really helpful if you make a sketch of it, because that sketch can reveal things that you might not have thought of. For instance, if it's a right triangle, well, we can use a whole lot of things with right triangles. Like we can use sine, cosine, tangent. We can use all the inverses. We can use Pythagorean theorem. There's a whole list of things that we can use, okay? And sometimes that can help. The second thing is we're going to write an equation involving all of those variables whose rates of change are either given or need to be determined. So we need an equation that's going to tie in all the stuff that we're given such that when we implicitly differentiate it, we have those rates of change. Then we do that implicit differentiation, and then we substitute all those known values in. Okay, so this is difficult. I'm not expecting people to immediately get it. You kind of have to work with simpler examples, moving to harder examples, and then you just kind of get the feeling of when you're doing something right. Okay. So that is all I have for this video. If you have questions, please let me know.